Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schenkelberg.
And this is Chris Jackson, and Fred and I were just talking about a question, interrogation from one of our listeners. Start with true or false. It feels like, 48 hours. Where were you on the night of X? But it's actually a good question or a good scenario they're asking us to get on top of. But should I read it out?
Yeah, go ahead and read it or paraphrase if you like.
Well, Johan Apinga, I hope I pronounced that name correctly, I should say. He writes, true or false, in order to estimate B50 ADCL, so that means to estimate essentially the median life with an 80% confidence level for a hypothetical 1 million cycle thermal shock test, I need 9 data points at 3 different thermal shock levels, 3 points per level. If false, do I need 3 points, 1 point per level? Also, how is thermal failure defined? Do you have the FEA guy look for thermal overload or thermal fatigue failure modes as a mean of designing the test? Thanks in advance. So there's a little bit to unpack there. Maybe we should just start at the start, which is Johan is trying to estimate the B50 / median time to failure with an 80% confidence level for a hypothetical 1 million cycle thermal shock test. First thing off the bat is, depending on what you're trying to do, B50 / median might not be the best metric to use, but be that as it may, should we talk at all about that one, or?
Well, yeah. Well, it goes to what we often talk about, and it sounds like that'll be part of the response to John is, what are you trying to show? If you're looking at when will failures be expected to show up, well, then median isn't enough. We need to know a little bit more about the variance or the density functions so that you get it. If you're looking for when will 1% fail, getting the B50 is not helpful.
No.
So it goes back to information that's not in the question. Is what are you trying to do? What kind of information do you need?
And just for our listeners, the median / B50, that tells you when you expect half of your, I'm assuming he's talking about bearings. I don't know, I could be wrong. But let's just say bearings, just to give it a name.
Shock loading, it sounds like it's some kind of mechanical system of some sort.
Yeah. Well, thermal shock test, all right. So cycle, thermal cycle, so you wouldn't do that for a bearing.
It could be electronics too, depending on the application. But be that as it may, we don't know. If you want to, see, I go back to why 3 different stress levels. If you have something that you're just trying to estimate it for this, whatever million loads or cyclic loads, what's wrong with the binomial equation with 0 failures? It doesn't give you the median, but it gives you could design it that way.
Yeah, but the binomial with 0 failures, that's still, I'd argue, is very inefficient when it comes to processing data. So you've got, yes, no, it's classic attribute data.
Yeah.
Did it last? Did it not?
Yeah. If that's really what you want, will this system survive this amount of loads with this kind of confidence? And then the only piece that's missing from it was what proportion. And he said, well, half. All right. Well, 50% at 80% confidence, and what kind of precision do you need? And you're off and running to the races, and probably can answer that sample size question pretty quickly.
So that's to estimate the median with lower 80% confidence level. I don't know. I don't know if I'd be on board with the binomial being the best approach. It's still that gives you probability of success more than anything else.
Right, but if that's all you need to know, then you're golden.
Oh, okay. Sorry, you're going back to, hey, if we understand what the decision is, and the decision is will it last versus what the median is, that's a better way of going. Is that what you suggest?
But if you want to understand what the median is, then we need to know a little bit about the variance.
Right. Well, that said, if you were to if you were to categorize, just do basic Weibull plot, and be able to characterize the shape of that probability density curve, you could estimate the median. But I suppose maybe our listeners, we're actually got a fair bit of assumed knowledge with our conversation, because this is all about accelerated life testing. And what that means is you're essentially trying to, for example, make 10 years worth of use equivalent to 5 days in the lab, hypothetically.
Or whatever,
turning the temperature.
Whatever they're doing with their acceleration, yeah.
Right, could be temperature, could be stress. It means you need to know the failure mechanism at play. And the reason why as a rule, if you're doing accelerated life testing, you want to have 3 different shock levels, is because it's always crucial that you confirm that you've got your model right. So to work out, okay, 5 days does equate to 10 years. Well, essentially, if you do 5 days worth of testing in the textbook, say, well, that's 10 years worth of effort, or worth of use, I should say. Well, okay, you can make lots of decisions, but you can make lots of really bad decisions as well, because your product is always going to be unique. And the idea about having 3 different stress levels is that it allows you to look at the textbooks and find the model which appears to best apply to your failure mechanism. And if the model predicts over 3 different stress levels what you would expect to see in terms of changes, then you can, with some degree of confidence, assume that model to be correct for your device. If the model predicts a straight line in terms of 5 days, this stress is equal to 10 years, then it gives you confidence that it's on the money.
And you're talking about the straight line is that you have at each of the stress levels, we have an estimated B50, a median time to failure or cycles to failure. And if that median, those 3 lines on a plot of cycles to failure versus stress levels, if that appears to be a straight line, then we have some confidence that straight line will project back to use conditions. If we're not invoking completely random or stupid failure mechanisms like go beyond a phase change or something like that.
And when we say phase change, the most obvious example of a phase change is when you increase the temperature so much that your product melts.
Yeah, or goes to steam.
or vaporizes, as Fred mentions, but it can be a little bit more subtle than that, because there's a lot of alloys out there with, the term eutectic springs to mind, where if you change the temperature, the microstructure wants to change its structure. And so essentially the alloy looks exactly the same, but at an atomic or molecular level, it is fundamentally changed, even though you can't see it. So it means that you're examining something that's not relevant. So that's why we want to have, that's at least the 3 different stress levels to make sure that your underlying model works, is applicable. A lot of potentially really good accelerated life tests have come undone by not doing that step.
Yeah, and I agree. Doing that step makes a lot of sense. It's prudent, especially if you got the resources and time to do it. But it's also, if you've got the prior knowledge, you already got characterization type stuff, the basic distributions, you can skip that. Mm-hmm. It really depends on how much you already know. But if you don't, and you're running this for the first time, 3 levels makes a whole lot of sense.
So, ball bearings are a really good example, I think. I know this is thermal shock. I don't know why I said ball bearing at the start. I just saw cycles and I went, ball bearings. And I'm actually using a ball bearing in a lesson, and I'm developing for a course right now. So I've got ball bearings in the mind, which is... But ball bearing manufacturers have a long history of making ball bearings. They should know those ball bearings inside and out, and they have a really good idea. No, they do. Let's not say that they should. They really do have a good idea about how their ball bearings are going to fail, which means that they're not coming at this a hypothetical accelerated life testing blind. They have a lot of knowledge. They might know exactly what the accelerated life model is for a ball bearing, because they've been doing this for 50 years, right? Which I think is what you're talking about.
Yeah, well, if there's prior knowledge, use it. That's one, what are you trying to do? To use prior knowledge, get the information you can. Now, there are circumstances, and I've run into it, where we have this new formulation, new technology, new widget, this new design, coupled with in an environment we just don't know how it's going to respond. So this thermal shock type cycling, that's a pretty rare environment that you get a million thermal shocks kind of thing. And that means very rapid, very big thermal differences that occur, like a 50 degrees C over a couple seconds kind of things.
Which is why you're thinking electronics, is that right?
Yeah, that's why I'm thinking electronics, but it could be whatever it is. I don't know what he works on.
Right.
But the idea is that there are circumstances where you go, we're going to push this into an environment or a situation that we just don't know how this technology or this new invention or whatever is going to respond. So then running 3 levels makes perfect sense to me.
Right. So, for example, the ball bearings that I'm fixated on right now.
Yep.
Maybe they're going to use those ball bearings in a very humid environment, which is not outside, which is, when I say humid, I mean really humid. And maybe they've used a special alloy, which is corrosion resistance or corrosive resistant, for example. But the reality is it's such a brand, even though they might know the technology very well, such a brand new scenario that they might go, you know what, we really need to make sure that our assumptions hold true.
That's right. That the corrosion resistance doesn't make it too brittle, and it doesn't do work hardening or whatever it does. And so let's run this test to find out.
Or the water doesn't do something weird to the lubricant that you didn't anticipate, or I don't know.
It will. Don't worry about it. It will.
Well, yeah, but but if people are asking those questions, that's where you go, you know what, we should do some accelerated live testing to see, if this brand new operating environment's going to ruin our day.
Yeah. All right, so then he gets to, I got 3 stress levels. And then part of that question, if I remember it right, which is what prompted me to say, hey, we need to record this, was 3 samples at 3 stress levels. Now, the hard part for me is if you know that you could have the time and or this capability to run all 3 samples and all 3 stress levels to failure, you'll get not great, but an okay estimate of the B50, right? If I run run it until I get 1 failure at each of those 3 samples, I argue that that's not a very good estimate of the B50. We're going to the first failure, which smacks more of, the extreme, what's the distribution that Weibull comes out of?
Yep, the extreme value distribution.
Extreme value distribution, yeah.
Actually, I'd argue it doesn't, because if you only got one, they call one bin or one group or one band, but that's only a single band, so there's no extreme values because the minimum's also the maximum at that level.
Yeah, if there's only one, yeah. But if you have 3 pieces running and you only use the first failure of each bin, then that's kind of the definition of the extreme value one. Ideally, you'd have way more samples, and then you have a better estimate of that leading tail. But that seems to be different than trying to find the median. Now, if the test runs to all 3 fail at all 3 stress levels, then I would say that's better to get a median value at each stress level.
Well, I'll tell you what you don't want to do, and that is get 3 failures at each stress level and take the sample median and say, that's the median estimate at that stress level.
I was going to do that. Why not?
Because when you only got 3 data points, essentially it's always going to be the middle data point. And because when you have such a small sample, if you ask a computer to randomly generate 3 numbers in accordance with any probability distribution, and you ask for such a small sample size, there's going to be huge variation in where the middle point lies. And I know the guy's asking for, Johan's asking for the median of the B50 live, but for the purpose of establishing or modeling the probability density function, I would argue is that you use the mean of each sample if you're going to just do a simple comparison, because the mean takes into consideration all data point values. And that will then help you create the PDF that you can then find the median from.
Well, the brute force do it by hand method is you, and you've seen the plots where you draw the probability density function for each stress level, and I might have 1, 2, or 3 failures for each, and what I'm looking for is that those distributions are equivalent at each stress level, similar
Correct.
shape, basically, or basic structure of them. They're not wonky from one to the next. They have similar variances. Is kind of what I'm going after there. The mean value or the median value will change because of the stress level change.
Right.
But the idea is that you can also analyze that with all 9 data points. In
Once
order,
you've got the,
I think
yeah.
that's what you're saying, is that use all 9 data points to get 3 estimates at those different stress levels.
Well, ideally, what you want to do is if you, I mean, I'm just using the means as because step 1 is to confirm you've got the right model, and that means essentially these 3 by 3 samples, when they need to essentially lie on the line that's predicted by your accelerated life model. And a good example is the Arrhenius model. And there's actually some plotting paper out there which called Arrhenius plots, which have the vertical axis, which is essentially how long it lasts, and the horizontal axis, the temperature, skewed and scaled in a particular way such that if that particular model applies, you'll see these 3 by 3 samples form a straight line on that plot.
Right. There'll be 3 clusters at that particular stress level.
Right.
But this only applies for steady state temperature.
The steady state temperature?
At
Yes, okay.
Right. So it doesn't really
right.
apply in this case where we're cycling with thermal shock.
No, but I just take, I mean, I just trying to, I know, this is in response to a thermal alt.
Right. Now, the idea, though, is valid, is that you can use all the points and you plot them on different types of models that you can use. And it might be a power law, it might be inverse, it might be this or that or the other thing. And you look for the ones that gives you the groups of 3 are roughly spread out equally. I'm holding my hands up going, right, they each about an inch in spread on a graph, and
Yep.
and then the 3 clusters roughly form a straight line that allows you then to lay a ruler on it. And I've done this manually, is you lay a ruler on it and that's your best fit straight line. And it's a regression problem where you can use various techniques for doing it. And it gets more complicated when you have sensor data. Then computers become very, very handy. But it's not a trivial regression problem. And
No, I agree.
Right, and that's where one of the things that prompted me, and this is the 333. Yeah, one, you're not going to get a great estimate of each mean or median out of just 3 samples. I agree with you. It's a small sample size if you treat those 3 stress levels as separate estimates of sample distributions. So gathering all the data, doing a more complicated regression analysis would will improve your sample size, essentially, or power. The other thing that I've learned years and years and years ago is that the lower stress level needs to be closer to your use condition, yet high enough that you're going to get some failures. And so part of the logic is you want more samples in that one that's closest to your use condition for 2 reasons. One, it's more informative than the 2 higher stress levels about what's going to happen at use conditions because it's closer in the overall stress profile. And because it's closer to it, it's likely not to create failures. So increasing the samples there helps you to get failures. And then you still might have sensor data. And then the 2 higher stresses end up helping you get that straight line estimate. And by having fewer samples, they influence the median value less.
So I think it's worth pointing out to your viewers that I don't fully disagree with you by any stretch of the imagination, but I do have a tendency to be a little bit more 3 by 3 than you. So maybe it's worth talking through why we have those differences. And one of my immediate reasons I love having 3 by 3 is that for the reason you talked about, even if you have a straight line in that hypothetical accelerated life model prediction, that's step one to validating the model. But if, as you point out, Fred, the 3 data points at the low stress level are nice and tight, but the 3 data points at the higher stress level are really spread out,
Yeah.
that's evidence to suggest that there is a change in failure mechanism as well.
Yeah. Yep.
And even the ability to extrapolate back from lower stress levels is entirely reliant on you understanding how that time to failure behaves once you go even higher stress to be able to go backwards. And so your take is that, well, the lower stresses are way closer to actual use conditions, and so there's an obvious benefit to having tests replicate the use cases as much as possible, which I can't disagree with either. But yeah, so I think,
well, it's a risk. It's a trade-off, right? Either way, we want to know if the highest stress levels are relevant. And one way to do that is do detailed failure analysis. Did this fail in the same manner as what the lower stress levels are doing or what we see in use conditions? And if not, exclude it. Take it out of the data set. Now you have 2 points. You always get a perfect line with 2 points. I always like that. But it's hard to get the confidence of it. Yeah.
That's why you need to have 3.
Yeah, that's why you have 3. You can throw one out if it's a different mechanism completely. Now, the other part is that if you do 3 by 3 and you see that, and it's looking at the residuals, right? If they're really spread out in the highest stress level, but very tight in the other one, I agree. It indicates that we're missing something in the model, and that's not accounting for it, or it's a different failure mechanism. And so you still got to do the failure analysis.
Yeah.
The very first accelerated test I did, which I talk about all the time, the first time we plotted the data, it was a difference in variance at the 3 stress levels. And I went and talked to a chemist about what was going on, what was happening in the device itself. And it was an oxidation process. And it was related to that the polymer chains softened. It wasn't eutectic at all. And the higher stress level we had was, I think, 30 C away from the melt point, which was too high. It started softening the shorter chains. They started to unravel. And so that the bulk polymer behaved dramatically differently than it did at lower temperatures. And so taking that into account, we changed the model of the analysis completely because using straight Arrhenius just didn't apply anymore because we were looking at completely different systems at the 3 different temperatures.
Right. So that's what you call critical thinking, Fred.
Well, I had some help. There was this university professor that I reached out to for some help, and he ended up introducing me to, what was it called? Wiener diffusion modeling, which is instead of doing looking at calculating means and stuff like that, and we looked at the change from one set. It was repeated readings, so we looked at the change in this magnitude of the change from one reading to the next, and so it was able to model a nonlinear structure or distribution, and so we ended up being way above my head how it all worked, but we ended up having a good time and actually came up with a pretty decent model that, as far as I know, they still use.
There you go. So it just goes to show how important it is to validate the model, or in some cases, create a model before you go making all sorts of really cool decisions willy-nilly.
Well, it was one of those things I'm looking at. It was the first time I did an accelerated test, and so I'm collecting data, and it was a non-destructive measurement system where I could take the samples and I could read them every day, every week, or whatever, depending on how much time we had. And it was pretty quick readings. And when I started plotting them, the first 3 points were pretty straight and pretty steep, which meant that this thing was going to fail in about 6 weeks. And 6 weeks out, it had leveled off. the curve, instead of being a 45-degree angle straight down and to the right, it started to bend and pretty much flattened out at some point. And I'm like, these will last a really long time. And now it's a matter is, does that degradation cross the line of where it's not going to work anymore? But that's where I started going to talk to these chemists, is what's going on? And it ended up being that the oxidation process on the surface of this material created a barrier for oxygen to get into the bulk of the material. So it slowed down the available oxygen.
Like aluminium or aluminum.
Yeah, exactly. And so it was, oh, that's cool. Why didn't you tell me about this a long time ago? But all the other testing that this organization did was they would take 3-4 points and draw a straight line through it and go, oh, that's good enough, and then chip it. And they were way underestimating the durability of these products for its temperature degradation.
Yeah, and that's an important point to emphasize, because a lot of people see reliability engineering as a cost, which you can always frame reliability engineering as a cost. It's always cost something to do some test or stop on your way to lunch and think about something before you just hit your multiple choice answer and then move on to the next challenge for the day. Mm-hmm. But it just goes to show if you do it well, you might avoid scenarios where you underestimate reliability, which can have equally disastrous effects from a commercial perspective to overestimating it.
Yep. Yeah. So anyway, it sounds like you've got and if I gathered it right, you got this question just as we were getting started chatting this morning.
Pretty much.
So that's cool. So it sounds like you got a couple of ideas to send Johan a couple of responses and ask probably a whole series of questions. And that's part of the process. If you're listening to this and you've got a question about what in the world are you guys talking about, or I have a question that maybe you guys can help with, let us know. Head over to accendoreliability.com/go/SOR. And there's a couple of ways you can find us there or get in touch with us there. Chris and I and the other hosts are available through LinkedIn or through our About pages. We have contact forms, and many of us have emails available and so on. So there's plenty of ways for you to get in touch. Let us know what you're thinking, what questions you have in your mind, and we'd love to hear from you and help you move forward with whatever you're working on, whether it's accelerated testing or something else. Let us know. So with that, Chris, I'll let you go so you can get a good response crafted back to this particular question.
Absolutely. Always a pleasure, Fred.
All right. And make sure you stress that you had to put more samples in the lower thing there. That's just me.
Well, the response might be, Fred says this, I say this.
That's right.
I mean, you work out what's best for you.
There you go. All right. Thanks, Chris. Talk to you soon.
Cheers, Fred.
Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.